Wine quality prediction with data mining. This lesson introduces data mining for machine learning using Python. We use the wine quality dataset to predict wine quality based on chemical properties. Data mining helps us find patterns and build models that can predict outcomes. Learning these skills is important for anyone interested in real-world analytics. Let us see how it works step by step. Running the cell now. What is the wine quality dataset? The dataset contains information about red wines. Each wine has features like acidity, sugar, pH, and more. The target is to predict a quality score between 0 and 10. This is a supervised machine learning problem. Running the cell now. We first suppress warnings. Warnings can appear as extra messages if there are potential issues, but are not errors. It helps beginners read cleaner outputs. Suppress warnings for a cleaner output. We import the warnings module, then ignore all warnings so the code is less messy. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. This code snippet sets up the environment by suppressing warnings and fixing the random seed for reproducibility. While it doesn't produce visible output, this ensures that any randomness in data processing or modeling will be consistent across runs, which is crucial for reliable experiments in our wine quality prediction task. Let us set up the data. We use pandas to load the wine quality dataset. The dataset is a semicolon-separated CSV file from the UCI machine learning repository. We show the shape and a few sample records so you see what it looks like. Data setup. We import pandas to work with tables of data easily. We set the URL for the red wine quality dataset from UCI. We load the semicolon-separated CSV using pandas. This prints how many rows and columns are in the dataset. This prints the first 3 rows as an example. Running the cell now. This output shows the wine quality dataset loaded into a data frame with 1599 rows and 12 columns, confirming we have a sizable and feature-rich dataset. The preview reveals key columns like acidity levels, sugars, and alcohol content, along with the target variable quality, which ranges from 0 to 10. This setup is crucial as it gives us a clear starting point for building a supervised machine learning model to predict wine quality based on these features. Understanding the data columns. Each row is a red wine sample. Features include fixed acidity, volatile acidity, citric acid, sugar, chlorides, and more. The last column is quality, our target to predict. Running the cell now. One important pre-processing step is to check for missing data. Missing data means some rows or columns are blank or incomplete, which can cause issues in modeling. We use pandas isnal and sum to get the number of missing values in each column. Checking for missing data. This code calculates how many missing, null, values are in each column of the dataset. Running the cell now. This output shows that there are 0 missing values in every column of our red wine dataset, meaning all features and the target variable qualities have complete data. This is important because it confirms that we can proceed with analysis and modeling without needing to handle missing data. It is helpful to view summary statistics of the data. This gives us an idea about value ranges, averages, and outliers. The describe method quickly shows useful statistics for each feature. Basic data statistics. Describe prints the average, standard deviation, minute, max, and other statistics for each column. Running the cell now. This output shows basic summary statistics for each chemical property in the red wine dataset, such as mean, standard deviation, and range, helping us understand the typical values and variability across samples. Notice that all features have 1599 entries, confirming no missing data, and that features like fixed acidity vary widely, for 0.6 to 15.9. This overview sets the foundation for exploring which features might influence the wine quality scores in our prediction task. Let us show all the column names so you can see the available features. This helps when deciding what to use for our model. Show all column names. We print the list of column headers. Each one is a chemical property or quality score. Running the cell now. This output lists all the column names in the dataset, confirming the features available for each wine sample. Notice how the columns cover various chemical properties, with qualities as the last column, our target variable. This overview helps us understand what data we have to analyze and predict wine quality. Data visualization, plotting wine quality scores. Visualizations help us see patterns at a glance. Let us plot how many wines have each quality score. It is a quick way to understand the target variable. Running the cell now. We use matplotlib to make a bar plot. The bar plot shows how many samples there are for each possible quality value. This helps us see if the classes are balanced or not. Bar plot of quality scores distribution. We import matplotlib for plotting. We count the number of samples for each unique wine quality score and make a bar chart. Set the x-axis label to show quality score. Set the y-axis label to count the wines. Add a title to make it clear what the graph is about. Show the chart on the screen. Running the cell now. This bar plot shows the distribution of wine quality scores, with the x-axis representing each score and the y-axis showing how many wines fall into each category. Notice the shape of the bars. Some scores appear more frequently, helping us quickly identify the most common quality ratings. This visualization confirms the balance and variation in our target variable, which is crucial for understanding the dataset before modeling. Visual exploration can reveal how chemical properties relate to quality. Let us compare the alcohol content for each quality score. A box plot makes it easy to spot differences between groups. Visualizing the relationship between alcohol and quality. We import Seaborn for nice statistical plots. We draw a box plot to compare alcohol content across different wine qualities. Set the plot title to make it clear. Show the plot. Running the cell now. This box plot shows the distribution of alcohol content for each wine quality score, highlighting how alcohol levels vary across qualities. Notice the trend in median alcohol increasing with higher quality scores, suggesting a potential relationship between alcohol content and wine quality. This visual helps us quickly assess how an important feature relates to our target variable, deepening our understanding beyond simple counts. Let us explore which features are related using a correlation heat map. Correlation shows how strongly two features change together. A heat map helps spot patterns in one picture. Correlation heat map of features. Create a larger figure for readability. Draw a heat map of the correlations between each feature. Add a clear title. Show the heat map. Running the cell now. This heat map reveals the strength and direction of correlations between all features in the wine dataset, with values closer to 1 or -1 indicating strong positive or negative relationships. Notice how this overview helps identify which features might influence wine quality, guiding us toward which variables to focus on in further analysis or modeling. Although this isn't the direct plot of quality scores, it sets the stage for understanding how features relate to each other before visualizing the target variable distribution. Preparing data for machine learning. We separate features x from the target variable y. Features are the columns used to predict the target. The target is the quality score. Running the cell now. Machine learning models need two parts: inputs, features, and outputs, targets. We drop the quality column from X and keep it only in Y. Splitting features and target. We remove the quality column from X so it only has the properties of the wine. We keep the quality column as Y. This is what we will predict. Running the cell now. Here, we have separated the dataset into features X and the target variable y. Notice that X contains all columns except quality, which is isolated as y, the variable we aim to predict. This separation is crucial for training machine learning models correctly. We divide the data into a training set and a test set. The model will learn from the training part, and we will check the accuracy on the test part. This prevents overfitting, which means a model only works on data it already saw. We use test size of 0.2 or 20% for testing and set a random seed for repeatable results. Split data into train and test sets. We import train_test_split from scikit-learn. We split the feature and target arrays into 80% for training and 20% for testing. Print the shapes to see how many samples are in each set. Running the cell now. Here we see the shapes of our training and testing feature sets after splitting the data. There are 1,279 samples in the training set and 320 in the test set, each with 11 features. This confirms our data is correctly divided for model training and evaluation, preserving the feature structure needed for prediction. Model building, random forest classifier. Random forest is a popular machine learning algorithm for classification. It builds many decision trees and combines their results. We use it to predict wine quality with the given features. Running the cell now. We choose random forest for this example. Random forest is simple, works well, and does not need much parameter tuning to get good results. We import the algorithm, create a model, and fit it to our training data. Training the model. Import random forest classifier from scikit-learn. Create an instance of the random forest model, set the random seed for consistency. Train, fit, the model using our training features and targets. Running the cell now. This output confirms that the random forest classifier has been successfully initialized with a fixed random state for reproducibility. It shows the model is ready to be trained on the wine quality dataset features, aligning with our goal to build a robust classifier by combining multiple decision trees. Notice that no training metrics are shown here yet. This step is just about setting up the model. After training, we use the model to predict wine quality on data it never saw before. We print the first 10 predictions to get an idea of the outputs. Making predictions on the test set. We use the trained model to predict quality for the test set. Print the first 10 predicted quality scores. Running the cell now. Here we see the first 10 predicted wine quality ratings from our random forest model on the test set. Notice the predictions mostly cluster around 5 and 6, reflecting common quality scores in the dataset. This output shows how the model assigns discrete classes based on learned patterns, helping us evaluate its classification performance. We now check how well our model did. Accuracy shows the fraction of correct predictions. A classification report gives more detail like precision and recall for each quality class. This helps us know if the model is missing or confusing any wine scores. Evaluating our model. We import accuracy_score and classification_report from scikit-learn. Calculate accuracy on the test set. Print the overall accuracy as a percentage. Show a detailed report for each possible quality class. Running the cell now. This output shows the random forest model's performance on the test data, with an overall accuracy of 66%, meaning it correctly predicts wine quality about 2/3 of the time. Notice that the model performs well on the most common classes, 5 and 6, with decent precision and recall, but struggles with less frequent classes like 3, 4, and 8, which have 0 scores due to very few samples. This highlights the importance of class distribution and suggests the model may benefit from techniques to address class imbalance. Random forest can tell us which features were most useful for predictions. A feature with higher importance means it has greater effect on our model. Let us plot this so you can see which wine properties matter most for quality. Feature importance plot. Import NumPy for number work. Get importance scores for each feature from the trained model. Sort features by how important they are for the model. Create a new big figure for the bar chart. Use Seaborn to make a bar plot of importance values, sorted from highest to lowest. Set the title to explain what we are seeing. Label x-axis as importance value. Label y-axis as feature name. Display the plot. Running the cell now. This feature importance plot shows which variables the random forest model found most useful for predicting wine quality. Notice how features are ranked by their importance values on the x-axis, highlighting the most influential predictors. This visualization helps us understand the model's decisions and focus on key attributes driving wine quality predictions. Now let us make it interactive. You can enter values for each wine property and see what quality the model predicts. Try to enter realistic values based on the earlier described output. Interactive, predict wine quality for your own sample. Create an empty list to hold the feature values you will input. Loop through each column name in the feature's data frame to get user inputs. Prompt the user to enter a value for the current feature and convert it to float. Add the float value to the sample list. Convert the list of input values into a NumPy array with shape, 1, number of features. Use the trained model to predict the quality based on the input sample. Print out the predicted wine quality score. Running the cell now. This output shows the predicted wine quality of 5 based on the user-entered feature values. The interactive code collects inputs for all model features, reshapes them, and uses the trained random forest to classify the sample. This demonstrates how the model applies learn patterns to new data for practical quality prediction. Mini project, try changing the input values to see what can get a high or low wine quality. What happens if you increase or decrease the alcohol value? Experiment with other features to see their effect. Summary: what we learned. We loaded the wine quality dataset and explored it visually. We checked for missing data and looked at feature statistics. We trained a random forest model to predict quality. We measured performance and checked which features are important. Changing feature values can change wine quality predictions. This is a foundation for many kinds of data mining problems. If you enjoyed this lesson, like and subscribe for more. Running the cell now. Next steps. Try other machine learning algorithms like support vector machines or gradient boosting. See if scaling the features improves the model performance. You can use the same approach with your own datasets. Leave a comment with your results. Running the cell now.